Nabin is going to present the Jiang et al. Paper. It's a good follow-on to this one.
Okay.
Oh, hang on. I need to take down. How do I stop sharing?
Have I not already shared?
I need to stop sharing.
I don't think you are sharing. I only see the
Yeah.
presentation.
Yeah, Nabin share
think
it.
Oh, Nabin is sharing. Okay. Hang on a second. Let me get your screen up. All right. Go ahead, Nabin.
Hi, everyone. I'm presenting a paper on improving AI system awareness of geoscience knowledge. This paper came out in 2020, and I think it has been quite influential in how we do physics and machine learning integration in hydrology. So yeah, let's move forward. And I decided to start with this one quote because the machine intelligence is the last invention that humanity will ever need to make. Because the idea is that in an ideal world, when machines start to do physics for us, then there is essentially nothing more to be done, right? So yeah, on the surface, it sounds like a pretty ideal world, but then once you dig deeper, you realize that the guy who said this thing is actually an expert on existential risk and doomsday scenarios, and he's written a big book on how AI could, end us all. So not always rosy. So I just put for thought. Now let's dive into the paper. And yeah, I've decided to organize it like this, but there's sort of uh, an unclear distinction between representation and regularization, I feel, especially when you're doing some integration between physics and machine learning. So I was kind of confused on what to put where, and just decided in the end to put everything in representation. So don't think it matters too much, but yeah, mention that. And also a nice AI generated image to start us off. Yeah, give me a second to enjoy that one. And okay, so introduction. Let's start with the idea behind why we need to combine physics and machine learning. So, like Umid said, physical models are based on theory that have been built over many hundreds of years. And more importantly to us, they are very interpretable. We can understand like what each and every variable means, how we interact with them in the world. So that's one key advantage of physical models. And machine learning models, on the other hand, they can fit data pretty well. That's like their big strength. They can fit pretty much any data, and that in turn gives us like more predictive capability. But on the other hand, there's very limited interpretability. They are like black box models, as Omid said. So the question again is that we need to, if there's some way we can get the best of both worlds and not sacrifice predictability without giving up, interpretability. So that's the key question that's also being addressed in this paper. And yeah, in this paper, they've given a few different ways on how you could go about doing this. I think this is pretty limited because, yeah, based on like just the papers we've done, we've reviewed today, I think we've come up with many different ways of doing this. But at least in this paper, they've given 3 different ways how you could go about doing this. So the first would be kind of similar to what we were discussing earlier, where not really, because this one is more about surrogate modeling, right? So in this case, what you're doing is your AI model is trying to replicate the physics-based model as closely as possible. So this would be like surrogate modeling that we discussed in when we were discussing the paper on transformers. And the next one is sort of yeah, this one we were talking about earlier, where the AI model tries to correct the outputs from the physical models and tries to learn the corrections. That is one way you'd go about doing this. And the final way is to just somehow kind of get a hybrid model where you can impose both physical knowledge and also your machine learning uh, architectures. And that is the method that they have adopted in this particular paper. Yeah, so the major objectives of this paper is, first of all, to integrate physics into recurrent neural networks to do hydrologic modeling. So yeah, catchment runoff modeling, that is essentially predicting stream flow. And they've also tried to build a global model that can transfer across catchments. Like this idea also, I think we came across when we were reviewing the paper on transformers, where instead of just calibrating your model at individual sites, you try to build a model, big model that can calibrate throughout the whole region, like throughout the whole United States, let's say, right? So that is also what they're trying to do here. And yeah, and then the final thing is that when you build this hybrid model, you can sort of probe the model structure because of the interpretability and get access to intermediate state variables. This one will probably be more clear when we get into it later. And yeah, the data they've used is Camel's data set for stream flow, for forcings, and for static attributes. And by static attributes, I mean like forest cover, your soil type, topography, so on. So it's a pretty popular data set in hydrology. So I guess many of us are familiar with it. And one other data set they've used is the NASA NICDC dataset for snow water equivalent, uh, which we'll come back to later. So, yeah, so now moving on to the representation, let's first start with the physics-based model that they've used. So they've used this model called EXP Hydro, and the model structure, from what you can see from the figure, is pretty simple. Like we have way more complicated hydrologic models than this, but at least for this paper, they've decided to use this. And if you sort of, let's say, forget the snowpack part over here, I'm just going to cross this off like this, then the remaining parts kind of looks like the simple linear reservoir model that we were discussing in our class earlier. But what they've done is essentially added a snowpack, and like the equations for a snowpack melting and rainfall partition are also like very, very basic. So yeah, this is the overall model structure. And yeah, this model has 6 parameters, I think, like down over here, you can see it's 6 parameters. And as inputs, it takes precipitation, temperature, and LD is the day length or sunshine hours. That's what you use. So yeah, this is just a very fairly basic hydrologic model. And yeah, the key thing about this hydrologic model is that the state depends on the input and also the value of state from previous time step. So if we move forward, this is kind of similar. Once again, I'm drawing the comparison to the linear reservoir that we discussed in our class. And yeah, one thing we discussed in our class is that when you have a dynamic model like this, you can kind of reshape them to look like a recurrent network, like a graph. And that is also what they have done in this paper is they've taken this EXP hydro model and then reshaped them to look like a recurrent network. And a brief recap on what a recurrent neural network is. So again, I was talking about this earlier. It takes state from an earlier time step, and then it feeds it into this big black box and then gets out the state value at this particular time step. And also there's this input at the particular time step and this output that we're interested in finally, right? So this is what your normal ordinary RNN looks like. And we were discussing something that looks like this over here on the right hand side. And if you unfold it, you will essentially get, when you unfold this thing, this functional form over here, that F over here, if you probe deeper into F, then it's gonna look like this over here, right? There's some sigmoid functions, there's some multiplication weights and biases. And this is your typical recurrent neural network. And what they have done is that instead of using weights and biases and activation functions, they've decided to replace it with the model equations F. And this is also again possible, as we discussed in our class, that we can take a dynamic systems model and then reshape it into to look like a recurrent network. And that is also what they've done. And they've called this network architecture, they've decided to call it PNN, which is I forgot like the full, they have really long full form for PRNN, but I just abbreviated it to physical RNN. So it's simpler, and also it makes more sense. So yeah, I think this is the key insight in the paper. Like the major point that they're trying to make in this paper is that when you have a system of model equations, you can turn them into a recurrent network. And yeah, that's the same thing I'm talking about over here. Like the weights and biases and the sigmoid functions have just been replaced by the model equations from the EXP hydro model. And the parameters of the recurrent neural network, which would be weights and biases, are also replaced by the 6 parameters that I was highlighting earlier. And yeah, the key idea I think is that this can be done for essentially any model, any hydrological, like a simple hydrological model. And yeah, the forward pass of this PRNN layer would essentially be the same as solving your EXP hydro. So the output that you get from PRNN is the same as solving EXP hydro. But the reason why they've reshaped them into this recurrent neural network architecture is that once you get this RNN, you can stack them between other neural network layers, and then you can do back propagation to train them using like common software interfaces. And yeah, this is also kind of a problem when we're trying to integrate physical models with neural networks. The problem is that you need a way to track gradients throughout the model. By tracking gradients, I mean you need a way to train them. And the easiest way to train them that we know of is back propagation. So an advantage of like reshaping the model into a recurrent neural network is that now you can do back propagation and you can train this thing now. And there are other ways to do this, but this is one of like, the fundamental ways of doing this. And the paper on transformers that we discussed a couple of weeks ago, they decided to use a surrogate model, I think. So they replaced the physical model by its surrogate, by its LSTM surrogate. And again, that will also allow it to be trained with back propagation and so on. And they also have used some CNNs all the way down here. So I think it's time to dive into the model architecture. So if you ignore the parameterization pipeline for a second, so what they're doing is this 5 things over here are your dynamic meteorological inputs, right? So precipitation, temperature, vapor pressure, and so on, like 5 dynamic inputs. And then they feed it into PRNN, which is essentially our EXP hydro model. And then you get this Q star, like the output there that they get is Q star, and they further corrected it using a couple of convolutional, one-dimensional convolutional layers to finally get Q. So this is again the model correction thing that we are talking about earlier. And yeah, there's some details like yeah, the conv1D layer has a filter length of 10, so its receptive field essentially goes back 10 days. So when you have this sequence of Q star, let's say it goes from 1 to 100, then when you're trying to predict that 100, you're going from 91 to 100, and you're essentially trying to learn some sort of mapping and checking if something at time step 91 can influence your output at time step 100. So that is what they're doing with the CNN. And also one key point is that when you have some model corrections like this, it could potentially help account for the structural inadequacies of PRN. You can also kind of see it from the pipeline itself that the conv1 detects 2 extra inputs, right? So solar radiation and vapor pressure. And these 2 inputs are not fed into PRNN because PRNN is pretty simple. Like the EXP hydro model is pretty simple. And if there's something to be learned from solar radiation and vapor pressure, then these correction layers will be able to learn them better. And next is the parameterization pipeline, which is also something we discussed in our paper on transformers. So the idea is that you try to build a global model that can account for site-specific attributes, like, for example, topography, tree cover, soil type, and so on. And then, yeah, you just train them across multiple locations, and then you get this big global model that has the potential to generalize to other ungauged regions. And yeah, for that, they've used simple fully connected layers. So these are just artificial neural networks that are fully connected, and each neuron is connected to every other neuron. So this is what they've used for parameterization. And yeah, in the regularization part, not a lot to talk about. So mostly the technical details of how many layers they have, how many parameters they have. Yeah, Adam's pretty standard, learning rate pretty standard, so not a ton to go into about it. I think NSE is what they've used for loss function, and they're training their models from 1980 to 1998, and then evaluating 2000 to 2010. Like this is what they're doing for models that they've trained on specific individual sites. And now going into the results. So yeah, results, they've categorized it into 3 parts. So this model performance part is when they're training it on individual sites. So I think this is kind of important to spell out because they're training one model at one particular site and then doing this for like every single site that they have in the CAMOS data set. And with regionalization, what you're doing is this is where you're trying to build a big global model, right? So now you're learning from every single point. And then finally, inference of unobserved variables, which we'll get into later. So this is the model performance on individual sites. And it's kind of interesting that the model performance actually beats LSTMs when you do not do the global model thing and you're only training on individual sites. You can kind of see that this hybrid DL model over here, there's NSE median NSE of 0.71 and LSTMs trained on individual sites as an NC of 0.6. So this I thought was very interesting. And yeah, also on other metrics, also yeah, the PRNN model is like pretty clear winner. And then moving to the next one, and this one is also I think really interesting.
Nabin, one second.
Yeah.
Yeah. So let's just make sure everybody's clear here. The bottom line is the LSTM model, meaning something analogous to Freddie Kratzert's benchmark, right? The second one above that, just to be clear, is a
so
what do
that's
they mean by
just the EXP hydro model, just a physical model.
It's called physical neural network. Okay, so that's the physical model. Okay. The one above that is if they don't use the physical model, they just use a neural network, correct?
Yeah, they just use the convolutional layers. Like,
Yeah.
so if you look at the architecture, if I can pull it up, yeah. So physical model would be only using this one layer. Then common neural network would be using only these layers.
Okay. So you see that they've done a pretty good job of benchmarking in the sense that they're testing all the combinations. And then finally, the top one is when they put the two together, right? But go back to your previous, the architecture, just so people are clear. This is everything without the parameterization pipeline. So you're training only the left pipeline. Yep, that means you train it separately on each catchment, and then you summarize the statistics of the results. So you're not actually using static attributes or using relationships, which are spatial. Okay, go ahead.
Yeah, so these are the results without the parameterization pipeline. And yeah, so yeah, I should probably also spend some time on these results. So yeah, the hybrid, when you combine both of them, you can see that they beat both just the physical part and also just the convolutional layer part. So you can sort of imagine that there's some sort of symbiosis going on where they are sort of covering up for each other. And this is, I think, more clear from this one table, which I thought was really, really cool. So what they're doing here is, okay, so they're training it on individual sites and then looking at the number of individual sites where the NSE has exceeded 0.55 when training the full model, like full hybrid model with both physics and machine learning. And then if you look at the respective thing, so this particular combination where just the convolutional, if you were to only use the convolutional neural network, you would get an NSE of less than 0.55 in that particular site. And if you use only the physical model, then also you'd get less than 0.55. But somehow combining both of them ends up giving you an NSE of greater than 0.55 in 16.5% of all sites. So this I thought was really interesting because, yeah, again, as I said, there's some sort of symbiosis going on between physics, which is some, and neural networks where they're covering up for each other. And yeah, again, this one is about yeah, the arid regions. If you look at the map on the right, so this big central block over here is pretty dry region. And around this region, again, over here, you can see that the model is also not performing very well. And by not performing very well, what this is measuring is the change of total runoff. By the change of total runoff, what it means is that when you get this Q star, so as we were discussing about earlier, you get some first initial measure, you get a Q star, and then you feed it to some convolutional layers, and then you get the Q, right? So if you compare the change between Q star and Q, then this also kind of gives you an idea of how much the neural network is covering up for the physics, right? So how much of overcompensation is going on. And in arid regions, you can see that there's a lot more overcompensation going on, which means that the physics model is somehow not adequate. And now we move to regionalization, the performance on regionalization. And now you can see that LSTMs are now leading the race once again. So they're 0.71, and hybrid model is 0.66. So the performance of this hybrid architecture is slightly worse than LSTMs, but the idea once again is that you have more interpretability, so you can sort of probe the inner state variables, and that could help you get some more insight into how the model works. So maybe this could be worth the trade-off in performance, right? So that is the case that the authors are trying to make. And this one, yeah, this one is one example of how you could go about doing.
Sorry, go back. That I think it's also interesting that if you look at the cases that fail where the Nash efficiency is less than 0,
Yeah.
they also mentioned that that model has less failures than the LST.
Yeah. I forgot about this. Yeah. This also, yeah, maybe somehow it's doing better in avoiding catastrophic failures. Maybe the physics is helping something like that. Okay, so this is an example of the added interpretability that you'd get from doing this integration of physics and ML. So this parameter f is one of the 6 parameters of EXP hydro. And if you look at the spatial distribution of this parameter f, so you can now probe this because you've done this whole hybrid architecture. So now you can look at how your individual parameters vary across space. So this is what you get for a distribution of f. And if you look at the distribution of sand percent in soil, then you'll see that f and sand percent, they match each other very closely. So now you get some idea of like this one particular parameter f could potentially be influenced by the sand percent, right? So now when you're going to new sites which are ungazed, you can just look at the sand percentage and then get an idea of how your model could behave. So this is one added bonus of doing physics plus ML. And yeah, this is the final thing, which I think, yeah. So what they're doing in this final step by unobserved variables is that in the original model, so we had 2 states, right? So first we had snowpack, and then we had some soil moisture over here, and snowpack was S0, this was S1. And if you now solve this model for the whole time step and look at what you'd get for S0 or S0, so that would be your snowpack. And if you go and compare it with some data set, like in this case, they've compared it to the NASA NICDC data set, and they've kind of observed that their model's internal state variable matches what you'd get what you'd get from the ground truth, right? Even though we never explicitly trained on snow, somehow the model is inferring like the correct patterns for snow, right? So this might not be very clear to observe, but there are some like so these particular regions over here. So this is where there's a lot of snow in the northern regions. And over here also you can see that I've highlighted them over there. The snow, like the S0 value is also high over there. So you can kind of see that the model is learning some physics. So yeah, that's it for the results. And finally, for conclusions, yeah, so this is their major point. I think that the integration of physics and ML can be symbiotic, where you have ML can compensate for the poor prediction, but physical models add more interpretability and more generalizability. So this is the key point. And another point that I also thought was interesting is that many hydrologic models can be reshaped into recurrent networks, and then they can be now trained by backpropagation and so on. And finally, also the inference of intermediate state variables also is very interesting. And finally, for the strengths and limitations. So yeah, this idea of conceptualizing it as a recurrent network, I thought was a really cool idea. And then they also give a proof of concept, many proofs of concept of interpretability. So I showed a couple of them in the paper. They have like a lot more examples of how you'd go about doing this interpretability. And yeah, for strength, I put in physics is not strictly obeyed. So that one I'll come back to at the end. And some limitations is that, yeah, it's kind of technical, but the system, the model, like the dynamical systems is generally a system of ordinary differential equations. And when you are reshaping them to write them as recurrent neural networks, you are essentially breaking them down to difference equations, right? So instead of saying ds by dt is equals to something, you are saying that s at t plus 1 minus s at t is equals to something, right? So this is essentially discretizing the ODE using a very, very simple method. There are more sophisticated ways about how you would go about doing this discretization in ODEs. And the major problem with doing this sort of Euler discretization is that it could cause some numerical errors that will keep building on throughout the time history. So I think that is one major limitation, and that's sort of where I'm interested in, and my research currently is also in how we can deal with this. And finally, is the last part is that yeah, the ML could end up overcompensating and dominating the physical parts. I think this, I don't know if Manuel is still there, but I think he has one paper where he's sort of comparing some, instead of taking your normal physical model, he's sort of changing it into a nonsense model, right? So instead of using proper equations, they've decided to use wrong equations to still see if the ML part ends up overpowering the physics, and if you still get the same results or not. I thought like that was a very interesting experiment done by Manuel. Maybe we can speak on it more later, but I think this is also a real danger that the ML part could end up dominating the physics. And finally, this physics is not strictly obeyed part is that when you have the model corrections, then the mass is not going to be strictly conserved. Uh, and this could also end up being a strength because if our model, let's say, is structurally inadequate, that by trying to force it to conserve mass, we are somehow getting like we have like wrong physical priors and we're sort of sticking to it. So that could also be a strength of this thing because by somehow allowing ourselves to free up from these physical constraints, we are also getting some insights into the model structure. Yeah, that's it. Thank you.
Thanks, Nabeen. That was a really excellent summary of that paper. Could you put back your strengths and limitations slide? Leave that up for a moment. So I think you've already done your short takeaway message thing. So let me throw it out open to people who have comments or questions. Notice that this is an approach where the neural network is still outside of the physical model. Yeah. So it's not that they have taken the neural network and embedded it directly into the physical model. What they've done is embedded the physical model into an overall neural network scheme so that the physics can inform the learning of the neural network model. And then they've also separated out components which have to do with the physics at a location and then the variation spatially, right, in a particular way. So they put in some particular regularizing assumptions about that structure and architecture, which helps to make the model more interpretable. Any thoughts on the second to last limitation, which is that in principle, if you're not careful, the machine learning part could overcompensate and dominate the physical part. What could or would you, in principle, should you be doing to help prevent that happening? I'm not sure if they actually did in the paper, Nabin. It's been a while since I read this, but do you have any comments or anybody else? And then maybe other people would like to add.
Yeah, I think they observed that in arid areas, you're kind of going away from the mass conservation, right?
Okay.
They're not really strictly enforced it, but
Okay. So the physical model obeys mass conservation, but the network as a whole is not forced to conserve mass in the sense of the earlier paper that Omid presented, where they were imposing, in principle, you could impose rules on the loss function requiring the entire model, right, to balance mass. In this case, it makes sense because we're not at all sure that the data at a particular location balances mass anyway, right? Okay. But what could you do to prevent the machine learning part from taking over and dominating over the physical part? In other words, sort of just ignoring the physics. What could you actually, in principle, what kind of strategies could you follow to help reduce that possibility?
I think like in the paper that Omid presented on, like incorporating the physics into the loss function, or incorporating, like, comparing the output of or yeah, so I'll leave it at that. Incorporating physics into the loss.
So putting some of the physical principles into the loss function, that's one possibility. What else?
Putting restriction on the weights.
Say some more, Mohammed.
Like the work that Yuan did. So this Rabi, he changed the structure of the whole model in a way that they consider some gates like recurrent neural network and put some restriction that the sum of the gates should be equal to 1 in that way. So the whole inflow and outflow from each cell could represent the mass conservation.
Okay, so can you go, Nabin, to the architecture slide again? Okay, so in principle, what you're talking about there, Mohammed, is that the PR and N part, the part that's the representation of the physics, you can impose different degrees of control on mass conservation in this portion of it. Okay, but there's still one more thing. Notice that you've got a physics component and you've got the rest of it, which is like a wrapper around the physics component. That's one way to think of it. What one single additional thing could you do to try to prevent the machine learning wrapper from just ignoring the physics model, in addition to some of the other things we just mentioned?
maybe you could do the reverse, like put the neural network inside the physical model equations.
So certainly you could put the neural network inside the physical model equations, and that's what Yuan did in his research. But another simple thing is, remember, the neural network has capacity, right? The more parameters and nodes you give it, the higher its capacity, learning capacity. So one way you can try to prevent the neural network from taking over is to control its capacity, right? So in Omid's talk, he showed you that they put L1 and L2 norms on the parameters. But in principle, you would just control the complexity of the neural network so that the complexity of the neural network didn't dominate over the complexity of the physical model, right? Because in principle, you could make the neural network have so much capacity that it can ignore completely what the physical model does. Manuel?
No, I was going to say that I think in this example, there's less risk for overcompensating, because I think in the only place that you would maybe overcompensate is in the convolutional 1D layers, because you're keeping them separate as separate components of the same model. But yeah, if you were to embed the network within the model, then the overcompensation does become a greater risk. And in those cases, I do agree that penalizing the complexity of the network might be one way to limit its capacity to, in a certain sense, overwhelm the physics model, because that's what kind of it does.
Yeah. So if you think of the neural network as a residual, which it's not, you could prevent it from generating a residual at all, and then it would be just a physical model, right? And as you add it, and in this case, it's not just a residual, because it's the neural network, as they showed, can just take the inputs, and you can throw away the physical model. Go to your results again, Nabin. This one, yeah. Yeah. So you can see the neural network model is basically you're throwing away physics, right? You're just learning a neural network model, and it's still not doing as well as the hybrid model. So in this case, you can argue that the machine learning model is not dominating, as Manuel pointed out. But I'm just pointing out that if you're concerned about the neural network dominating, then one way to do it is to try to control its capacity. Yeah. Okay. Any other thoughts or comments before we move on? Okay. So the last, go ahead and take that down, Nabin. Thank you.